Hello, Section 43. Today I'm going to be talking about the topics of tomorrow's TerrNav quiz. So we're going to start with the basic AToNs. I'm just going to go through all of them, explain them briefly, just so you have a general understanding of them. So the first ones that we're going to start with are these. These are called cardinal marks. They're called cardinal marks because they mark a cardinal direction that you have to pass. So the best way to explain this is if I go to the next slide. If I've got a danger here, this buoy with these two cones pointing north, which is seen here, is telling me that I have open water to the north of me. Here, the cones pointing down tells me that I have open water to the south of this wreck. Here, this egg-shaped, you can remember that because it's east, tells me that the open water is to the east of whatever this wreck is, or obstruction or whatever it is. I'm using a wreck as an example. And then to the west, you have this kind of wine glass shape, and that's how you can remember it. West is a wine glass, right? And those are all seen here. You have the east, north, south, and west. And you want to make sure that you are passing that direction of these buoys. Next up, you have the lateral marks, 5 through 12 here. And there's always going to be cans and nones. Now, regardless if you're in the A or B system, the cans will always be on your left side, your port side, when you're going into a port, and the nones will always be on your starboard side when you're going into a port. So in the B system, red right returning, so the red none is going to be on your right side when you're returning, and this green can is going to be on your left side when you're returning. In the A system, it's the same situation, except the none is green and the can is red. So you're still keeping this none, even though it's green, to your right side, and you're keeping this can, even though it's red, to your left side. Now down here we have preferred channel marks. So the color of the top band is going to tell you how you should treat that buoy if you want to be in the preferred channel. So in the A system, this looks like a none, because you're going to treat it as a none if you are using the preferred channel. So the best way to show that is over here in this slide here. As you see, we have red, green, red. So this is saying there's another channel going this way. You can take it if you want, but the better preferred channel is to go this direction. And in that situation, you're going to treat this as the red buoy that are the red buoys that are all going up this way. If, for example, I wanted to go this direction, I would treat it as a can. So I would keep it to my port side, but if I want to go this way, I want to keep it to my starboard side. It's all about the color of that top band. So in the A system, a preferred channel that is to port is going to have this as the symbol, and a preferred channel to port in the, if I misspoke, in the B system, preferred channel to port, you're going to be using this, and in the A system, because green is red in the A system, this is going to indicate a preferred channel to port. Now in the B system, this would then indicate a preferred channel to starboard, because remember, green, you're treating it like a can, and in the A system, same deal, just it's red. A little complicated. That's probably the most complicated of the lateral marks, but hopefully this diagram here makes a difference. So for example, if this was the A system, all these buoys would be green, all of these green buoys would be red, and this would have the top color green, the middle color red, and the bottom color green. So next up, this little fancy buoy here is called a new danger mark. And what it marks is something that just recently became a danger. So something sank, a week ago, and they haven't been able to go out and survey it to see if they can remove it or not. And so that mark's going to go there saying, hey, there's a danger here, we don't know a lot about it, just stay out of the way. Let's say that danger was surveyed and it was determined that there was nothing that could be done about it, that danger was going to have to stay there, like it was a shipwreck that couldn't be moved or something like that. Then it would get replaced with this isolated danger mark over here. That means there's an isolated danger here, go around it. This buoy here means safe water, and that means that you can pass that buoy on any side, you're not going to run aground, you're done. You're basically out of whatever channel there was. And so you can see that here. So if I am going, the best way to think about safe water marks is if you're leaving, right? So I've got this channel here. I have to stay between these buoys. If I go outside of these buoys, I'm going to hit land. Outside, I'm going to hit land. There's an isolated danger over here. I got to keep clear of that. And now eventually I'm out in the open ocean. I'm not in this channel anymore. There's no more red-green buoys. I've hit this. And this is telling me, okay, now I'm safe to go wherever I need to go. This is a a special mark, and they can mark a variety of things. I primarily see them marking anchorages. I've seen them marking security zones by airports too. Yellow buoys can also be weather buoys. I've seen yellow weather buoys, but they just have a special purpose, and that purpose is very generalized. You're not going to see them on here, but it's just something to know about. This is a mooring buoy. I have never seen a mooring buoy in this format before. They're usually spheres, but they're going to have that blue and white combination. This is a information or regulatory mark, so that's going to give you information like speed limits. It might give you a danger area, in which case it's going to have a triangle on it. It might give you an exclusion zone, in which case it's going to have, if I said triangle, diamond, it's going to have a diamond with a cross on it. So it's got like a diamond shape like this, and then there's a cross. And that's basically that. Not too much to know about those. You primarily see them in like small buoy format that look kind of like this in near shores and beaches and stuff like that. But I've seen like full-on versions of those that look like green cans painted white with those symbols on them. So just something to know about. So these two symbols here are something that's put on a lateral mark, like one of these, in the intercoastal waterway. And the reason that's necessary is sometimes the intercoastal waterway is going to hit another channel. And when that happens, the aids to navigation for that channel might be different than that of the intercoastal waterway. And so we need to specify what the intercoastal waterway people need to treat those aids to navigation as. And that might be a little bit confusing, but I'll explain it right now. So you can see here, this green can has a square on it, you're treating it like a can. That red nun has a triangle on it, you're treating it like a red nun. Same deal here, same deal here. Oh, whoops, I have green on both sides. Well, which one am I treating as green, which one am I treating as red? Well, here, I'm treating this one as a red because it would follow the trend here. So that's got a triangle on it, this one's got a square on it. And those are dayboards, by the way, but you're going to see the same thing on buoys too. So here we come up, oh, I have a red buoy. Isn't there supposed to be a green buoy there? Well, yes, there is. And so the way we mark that is that little red square there, treating it like that green buoy. And over here, again, that red triangle, treating it like the red buoy. And then this green buoy has a triangle on it because it's telling you to treat it like a red. That's that. Just use along the intercoastal waterway so that people don't get confused when suddenly it stops being green and changes red for apparently no reason. And it's because of that other channel. These are dayboards. They look just like these. These can be of any color. So these are some color possibilities that dayboards could be. And on your chart, they're going to be written as K, indicating that it's a dayboard, and then the color of the first two bands. So, or the outer two bands followed by the inner bands. So in this one would be KGW, this would be KWR, and this would be KBG. And for these, for example, this would be KRW. So that's all there is to these. Down here, we have what a dayboard would actually look like in practical use. And if we go over here, we can see that. So the idea is that if you're going to enter this channel, you need to be aligned. And so these dayboards align you if you have them vertically aligned. So if you can see them one stacked above the other, you know that you're heading in the right direction. Well, what if we're off to the side? Well, if my big backboard is off to the left side and the smaller board's to the right side, I know that I'm left of the channel and I have to go right. If the small board is off to the left side and the big board's off to the right side, I am far to the right and I have to go left to get back to here. Okay, so next up we're going to have some light characteristics. Now there's a ton of light characteristics, these are just the most common one. So we're going to start, this is called composite group flashing. It's called that because it's flashing in a group. So it's going to flash this pattern 1, 2, 1, 1, 2, 1, 1, 2, 1 over and over and over again. This is special because these are what these cardinal marks flash. And so that's done in a clock system. 12 o'clock, although it doesn't flash 12, it just flashes very quickly, would be indicative of a north buoy because, you know, if you're thinking clock faces, right? An east buoy would be 1, 2, 3, and then flash. And then a south buoy, which is what this is indicating, is 6, because think about it as 6 being south on the clock. And then a west buoy would be 9, 3, 6, 9, and then that. And that's how you can identify just using lights a cardinal mark. This group here is called occulting, and the characteristic of that is a light period that's longer than the period of darkness. So you're going to have light, dark light, dark light, dark light, over and over and over again, with the dark period being significantly shorter than the light period. This is called isophase, and it's just equal periods of light and darkness. This is just called plain old flashing. This is called group flashing. Again, contrary to composite group flashing, there's like different stuff going on here. It's just groups flashing 1, 2, 3, 1, 2, 3, 1, 2, 3, over and over and over again. This is called long flashing. It's called that because there's a long period of time between the lights. And then this is a fixed light because it would just display a constant beam of light. So that's Crash Course on AToNs. Okay, so now we're going to learn about the visibility of lights and how we calculate that. So I've got a little pony here. It may or may not be the homework. Please don't copy my answers. You should actually understand what's going on. So I know to calculate my geographic range, which is the range that, with perfect weather conditions, whatever, I should be able to see that light, given my height and the height of the light. So we're going to take the height of the light, which in this case is 70 feet. We have to figure out the distance on the horizon, which is found by 1.17 times the square root of 70. And then I have to add that to whatever I can see, because if I can see up to a certain amount and that light ends there, I can technically see that light. It's confusing. That was a very confusing explanation, but you understand where I'm coming from. So 1.17 times square root of 70, and then my height, which is 65, so 1.17 times square root of 65. Take those two numbers, add them together. That's going to give you that geographic range. Now, that can also be found in Bowditch. Bowditch is going to give you a table for that. So table 12. So let's go take a look at table 12. Here's table 12. So I know that I was at a height of 65 feet. Well, there's 9.4. And I know that the other one was a height of 70 feet. There's 9.8. Add those together. What do you know? You get the same answer I got. So same deal with this down here. Exact same procedure that I just went over. Except now you can do it using table 13. That's another option. And the way that you would do that, you go over to table 13 here, you say, okay, so my height of I is 32, we'll call it 33. 33 feet, and 57 is where the height of the light is. So I just got to figure out where 57 here and 33 here intersect. Now, it's not going to be exact. You could probably do some interpolation, but it's going to get you pretty damn close. So 57, we'll call it 56, and 33, that gives you 15.7, which is pretty close to that 15.5 that I had. So now I'm going to have to compare the luminous range of a light to its geographic range. So we can find geographic range using what I just talked about, but now we got to figure out the luminous range, and that's where this little thing comes into play. So if I've got a light with a nominal range of 5 miles and my visibility is 1 mile, well, my nominal range is 5 miles, my visibility is 1 mile, well, I just got to figure out where that 1 mile and this 5 miles intersect. So if I follow that back, if I just go up this 5 here, oh, it's going to intersect right there. And obviously you would use your triangles for this to get everything perfect, and it's not always going to line up exactly like this has. Go across to here. Well, what's that? That's like 1.4. It's a little below half. So that's going to give me a luminous range of 1.4 miles. So given the luminous range being 1.4 because the visibility is only 1 mile, and the geographic range being 12 miles, I'm not going to see this light until it's 1.4 miles away from me, because it's always going to be the lesser of the geographic and luminous ranges. So that's just leaving you with a visual range of 1.4 nautical miles seen here. And the rest of these problems are just the exact same thing I just did. This last one is a little tricky because you have to do some interpolation. And so the way you're going to do that is if something doesn't lie exactly on one of these lines, because about 100% of the time it's not going to happen, you're going to use some interpolation. So the way you're going to do that, in this situation we know that the nominal range was 13 miles and the visibility is 17 miles. So my nominal range is 13 miles, so 15, 14, 13, 15, 14, 13 right here. And I know that I'm at 17 nautical mile visibility. Well, there isn't 17 nautical miles here, but I know it's somewhere between here. So I'm going to measure the distance at 13 between this line and this line in millimeters. And then I'm going to multiply that by the ratio of however far it is from the bottom number, 11, so 11 to 17 is 6, you see a 6 here, to the distance between this one and this one. So this is 27 to 11, that's a difference of 16, so it's going to be 22 millimeters, because that's what the distance was, times 6 over 16 gives me 8.25 millimeters. So that tells me that to find the luminous range, given a nominal range of 13 miles and a visibility of 17 miles, I have to go between here and here, I have to go 8.25 millimeters up. And so when I do that using my rulers and my triangles and all of that jazz, I'm going to go across and I'm going to see that it's going to be roughly 17.2. I know the answer key I think has it higher, like 17.5, but I got 17.2, and that's fine. So I know in this situation, my luminous range is 17.2 miles, but I'm restricted by my geographic range telling me that it's only 12.9. So in this situation, the geographic range is going to win, and that's going to be my visual range, because that's when I'm actually first going to see it. That's a crash course on visibility of lights. So now we're going to move on to midlat sailing. I'm going to go through it fairly quickly because you guys should probably already know how to do it. We're just going to rush through it, all right? Okay, so I've got a problem here. These are straight from the homework. I've just written them out here, made it a little bit neater. Sorry for my bad handwriting, just you're going to have to deal with it. So this is a course and distance problem. So I'm given a latitude 1, a longitude 1, a latitude 2, and a longitude 2. So I'm going from north to south, so I'm going to have to add those together to get my L. So you add them together, you get 62 degrees, 42.5 minutes south, because I've gone south. Convert that to minutes, because we're going to need it later, gives you this. Now I'm going to figure out what my mid-latitude is, and the way I'm going to do that is I'm going to take my L, I'm going to divide it by 2, and then I'm going to apply it to either north or south, whatever's easier. I know that I end more south than I was north, so my mid-latitude is going to be in the south. So it makes a little bit more sense to work with that south number. You could do it with the north, it's just going to be ugly, so don't. So I'm going to take this number, I'm going to divide it by 2, I'm going to get this. And now I'm going to take my latitude 2, which is in the south, and I'm going to subtract the mid-latitude from it, because I know that the mid-latitude is going to be somewhere over here, which is going to be halfway between these two. So I'm going to subtract it, I'm going to get this, which translates to this in decimal format. So I've got that number, I can't do much with it. Let's go find my DLO. And so the way I'm going to do that is I'm going to, because I was west, I went east, I'm going to add them together. I went so far west that I went east. That's just the way I like to think about it. You add them together, you're going to get this number. Well, oh no, that's above 180. That's not possible. Yeah, it's not possible. So you got to subtract it from 360 to get you this value, and that's how far you are west. Convert that to minutes, you're going to get this. And I know that in order to find my course angle, I need departure. I already have L, but I need departure. And I know that that formula is going to give me departure. Well, I just found DLO, and I happen to know what my mid-latitude is from here, so I can do departure is equal to DLO times the cosine of my mid-latitude, which is this, and that's going to give me that many nautical mile departure. I'm now going to plug that back into this equation. So to find CA, I have to take the inverse tangent of whatever's going on here. And so you take the tangent inverse of P, which is this, over L, which is that, which we found up here, and that gives you a course angle of 62.39431 degrees, and it's south to west. I know that because I went south and west. So now I have to figure out what that is true. Well, I know that if on a compass rose, you have north, you have south, you have east, you have west. South is 180 degrees, and I know I went west 62. So I take 180 plus 62, that gets me this, and that's my true course. So I found that now. Now I need to find my distance. And distance is going to be L divided by the cosine of the course angle, because you think about it, you multiply that D over here, divide this over here. D is going to be L, which we know is that, because we found it from earlier, divided by the cosine of the course angle, there's course angle, and that's going to get you that many nautical miles. That's your course and distance. So the second type of problem for mid-latitude sailing is position of arrival. And in that situation, you're given a latitude, longitude, how long you went, and what direction you went. So our latitude 1 is this, latitude 2 is this. Our course angle is south 80 to west. I know that because 260 minus 180, right? Because we know that due west is going to be 270. So 10 less than that is 260, which is 80 degrees west of south. Now, right off the bat, I can find my L, because I know that L is going to be cosine of the course angle times D. Well, I have D, I have the course angle, so you just do D times the cosine of the course angle, gets you 100. You can't quite read those decimals there, which is to convert to that in degrees and minutes. And we know that we went that south from this north value, so I got to subtract, again, I did longhand here, so it's a little difficult to see, but I took that 40 degrees 36.0, subtracted that 1 degrees 40 from it, and then I get that value, and that's my latitude 2. That's the easy part done with. Now I got to figure out what my mid-latitude is, because that's going to come into play with departure and figuring out my DLO and getting my longitude too. So I got to take this value, I got to divide it by 2, which is 0.5 degrees, 20 minutes, but 0.5 degrees is the same as 30 minutes, so it's just 0 degrees, 20 plus 30, which is 50 minutes. And I know that I'm still going south from here, and then you just subtract it to get this. Because if you think about it, this is going to give you half the distance to here, which is your mid-latitude. So that's this, and we don't care about it in this format. We want it in degrees format, so we're just going to convert it to degrees, gets you this. Now, I need departure, because I need to figure out what my DLO is. So departure, we know, is L times the tangent of my course angle. So we have L from here, we have the tangent of the course angle, that's going to get me that many nautical mile departure. And we know that DLO is going to be departure over the cosine of the mid-latitude. So you take departure here over the cosine of the mid-latitude, seen here, gets you this. Now I got to convert that to degrees minutes, gets you this. Got to round that up because this is super close to 18.0, so just round it up to 18.0. And I know that I'm going west. Well, my initial position was west. I went more west, so I'm just going to add that west value to get my longitude too. So that's a crash course on tomorrow's quiz. I hope you found that helpful. I know I go quick, I talk fast, but rewatch as many times as you need. Ask me questions if you need, and I'll try to help you in the best way I can. Thanks. Bye.